Okay, as we discussed in the previous video, a parallel plate capacitor, which is the most common type that's used in circuits, consists of two sheets of metal. And in a real capacitor, there will be a layer of plastic that separates the two sheets. So here in green is the layer of plastic that separates the two sheets. That layer of plastic gives you several different advantages. One of them is that when we use the capacitor, there will be positive charge on this top part, on the top plate, negative charge on the bottom plate, and those opposite charges, they're attracted towards each other. And so if we didn't have the plastic in between, they would just slam into contact with each other and the capacitor would be discharged. So that's one advantage. So this is advantages of plastic. Advantage number one is it provides mechanical support to keep the two plates separated. Advantage number two has to do with dielectric breakdown. So this is a phenomenon that we have discussed in a previous lecture. It's a cascade process, so we've discussed this in terms of air, where an air molecule that is subjected to a strong electric field gets stretched. So in this case, we have an electric field pointing away from plus towards the bottom. Air molecules can be stretched by that field, but so can the molecules of the plastic. And if we turn up the field higher and higher by adding more charge to the top plate and more negative charge to the bottom plate, eventually we will rip loose an electron from an atom. The electron will be accelerated upwards. The remaining positive ion will be accelerated downwards. They smash into other atoms that are already under electrical stress from this field, and they can cause those to have their electrons ripped loose, and we get a cascade process. In air, after the electron and the ion are separated, they travel a significant distance before they smash into something else. And so that gives them a chance to absorb a lot of energy from the strong electric field. In a solid like this, that doesn't happen because there's so many atoms in it that the electron and the ion only accelerate over a very small distance before they smash into something else. That interferes with the cascade process, making it harder for a plastic to undergo dielectric breakdown than a gas like air. There is a critical field above which dielectric breakdown will occur, and the critical field for air is about 3 × 10⁶ volts per meter. But the critical field for a plastic like polystyrene, which is one of the ones that's used in the manufacture of capacitors, is much bigger, about 25 × 10⁶ volts per meter, because there's less space for the ions to accelerate, and so that means that the cascade process gets quenched to a certain extent. Now, that's advantageous to have this higher critical field, because when we are using capacitors, often we want to be able to store a lot of energy in them. And as shown in a previous lecture, the potential energy that's stored in the capacitor is 1/2 CV². Now, as we talked about in the previous lecture, the voltage difference between the top and the bottom plates of the capacitor, for a parallel plate capacitor, that's related to the electric field in a very simple way, that the voltage is simply the electric field times the distance between the plates. And it's so simple because the electric field is uniform and constant in value, so we can just multiply the electric field times the distance instead of integrating. So we can see if we want to store a lot of energy, we want the voltage to be high, which in turn means that we want the electric field to be high, but we don't want dielectric breakdown to occur. So a material with a higher dielectric breakdown is going to be beneficial for us. When you purchase a capacitor, it will tell you a maximum voltage, maximum rated voltage that you can use. And if you go beyond that voltage, there's a chance that you'll have dielectric breakdown. And you can see how that rated maximum voltage is related to the critical electric field and the distance between the two conductors. So using the plastic allows you to store more energy in the capacitor simply because it allows you to get to a higher voltage. But it helps you in a third way, which is due to the effect of the plastic on the total electric field. So let's draw a side view of our capacitor, and we'll zoom in just on a part of it and look in the side view like this. So I've got these positive charges on my top plate, negative charges on the bottom plate. Put those together, their effect is to create an electric field due to the plates, which we'll call E plates, like so. That is going to polarize the molecules of the plastic. Now, we talked about the sort of limit of tearing electrons loose. We're not going to get into that limit, but still we're going to be polarizing them. The nuclei, I'm going to not really draw things to scale, but the nucleus of a particular molecule or a particular atom will be pushed downward by this electric field, and the electron will be pulled upward because the force on the electron is opposite to the electric field. And that's going to happen to molecules throughout the plastic. So I'll just draw in a few of them, like so. So again, the minus is pulled to the top, the plus is pulled to the bottom. Now you can see that in the interior, we've got a bunch of plus and minus charges all very close to each other. And so their effect is to cancel each other out. But along the top surface, there's a layer of negative charges that's not canceled out. And along the bottom surface, there's a layer of positive charges that's not canceled out. So I'm going to redraw it, showing just those two layers of charges due to the polarization of the plastic molecules that don't get canceled out by the proximity of opposite charges. So here again, we've got the positive charges in the top plate, the negative charges in the bottom plate. I've got a layer of negative charges along the top due to the polarization of the plastic, and another layer of positive charges along the bottom. Let's think about what happens to the total electric field. So I have the electric field due to the plates. It's going to point like this. But now I also have an electric field due to the surface charges of the plastic. And now I've got the positives on the bottom instead of being on the top. So the electric field due to those surface charges is going to point upward. E surface points upward. It's not quite as big as E plates, but it's pretty close. In fact, I'm going to define the dielectric constant. Dielectric constant. Kappa. That's the Greek letter kappa. It looks a lot like a K, but I'm trying to draw it slightly differently with a little bit of slant to it. Dielectric constant is defined to be the electric field due to the plates, the magnitude of that divided by the total electric field. So here we can see the electric field due to the surface charges cancels most of the electric field due to the plates, and so that's going to leave a total electric field that's much smaller than the electric field due to the plates. Therefore, if we're inside a plastic, kappa is a number that's pretty big. In fact, for polystyrene, kappa is about 2.6. So that is to say the electric field, the total electric field between the capacitor plates is reduced by a factor of 2.6 by the effect of the polarization of the polystyrene molecules. Now, what effect does that have on the capacitance of this capacitor? Well, we could calculate the voltage between the two plates using delta VAB equals minus the integral of E dotted into dr, evaluated along some line from A to B. So like some line from a point here down to a point here. We just said that all along that line, the electric field is reduced by this factor kappa, reduced by a factor of 2.6 for polystyrene. That means that the voltage, since the electric field is reduced, the voltage is also reduced by the factor kappa. The capacitance is defined to be the charge on the plates divided by the voltage. So if the voltage is reduced by the factor kappa, the capacitance is increased by the factor kappa. And that's a good thing. Most of the time we want big capacitance. For example, if we're storing energy, large capacitance helps us to have more energy stored. So we can see from this that the capacitance of a parallel plate capacitor, if we include a plastic in between the two plates, is the result that we got before, the area of the plates times epsilon naught divided by d, multiplied by the dielectric constant of the plastic between the two plates. So that's the third advantage of putting the plastic between the two capacitor plates.